Okay, so here we have the pre-governors portion of the sample test for Algebra 2 for Unit 1. All right, for question number 24, they want us to draw a graph on a coordinate plane, and they've given us one down here in A, to symbolize the path of the support cable of a suspension bridge. So we've got a little picture of a suspension bridge over here. So we have the two towers, and these two towers on the bridge are 80 feet. And then there is a distance between the towers of 350 feet. It says the cable reaches its lowest point at the middle of the span. So right here in the middle of the span, that distance is 22 feet. Don't ask me where 15 came from. 22 feet above the bridge's surface. So we're supposed to draw this. So I'm going to put my axes right here when I draw this, and I'm going to come down here. So this, my y or vertical axis, is going to be the height, which is going to be marked in feet. So I'll write that down. And over here in the x direction, this is going to be the width, and that is also going to be marked in feet. So my cable starts out up here at a height of 80 feet at the top of the tower, and then it drops down and comes back up to a height of 80 feet again. So this whole distance right here took 350 feet to go across. The other important point I want on here at the middle of my bridge, it was 22 feet off the ground, and that would be in the middle. And if I go from 0 to 350, half of that would be 175. So 175 is in the middle. It says to draw the graph and be sure to label your axes, which I did, use an appropriate scale, which I did, and give the coordinates of 3 key points of interest on the graph. So this point right here, the coordinates would be 0, 80, over 0, up 80. This point, my minimum, would be over 175, up 22. And then the point at the top of the other tower would be over 350 with a height of 80. All right, so my next question, part B, I'm supposed to write an equation of the function to model the cable's path. Let me scooch up a little bit here. So this is a quadratic function. So I'm going to start with y. I know I'm going to have a number that stretches on the outside of my parentheses. It's a squared because it's a quadratic. It makes a U shape. My x, in order to move over here, I want to move to the right 175. So my x is going to be minus 175. And I also need to move at this point up 22 units to get to my vertex. So I'm going to have a plus 22 on the end to move me. The problem is I don't know what this a is right here. But I do know that I have some nice points on the graph. The easiest point for me to look at is this one that when x is 0, y is 80. If I plug in 0 for my x, okay, I'm going to leave my a there. Then I'll plug in 80 for my y, because I'm putting in the point 0, 80. Now I have an equation with only one letter left in it, the a. So I can simplify this and figure out what a is. So I have 0 minus 175 is negative 175. If I square that, it gives me 30,625. So now I'm going to subtract 22 to move the 22 to the other side. And then I'd need to divide both sides by the 30,000 number. So my a value is going to be 58 over the 30,625. I'm not going to go ahead and do anything, turn that into a decimal. If it were a fraction that reduced, I would reduce it, but it doesn't, so I'm going to leave it that way. So my final equation, y is 58 over 30,625, x minus 175 squared, and then the plus 22 on the end. All right. Question C says, another suspension bridge's cable is modeled by that function. So now I've got y equals 3 1,000ths, and then x plus 100 squared, and then a plus 10 on the end. So it says compare and contrast the bridges. So what would these two bridges have in common? If I compare, I'm saying what they have in common. So both bridges make a U-shape. Are parabolas or U-shapes. So I'm going to say the shape is the same. Okay. Okay. So that's comparing them. That's really sort of the only thing they have in common, except for that both of them, the suspension goes up. I could also say that as well. Let's contrast them. What do they have that's different? Well, I can look at this number on the end, the 10 there. What is that going to do that's different? The second bridge has a cable that hits closer to the bridge. Okay. So the first bridge had a height of 22. The second bridge is just going to have a height of 10 right there. Okay, let's see what else we could say. What about this plus 100? So that means the second bridge, is to the left of the axes instead of the right. And it is what? Is this going to be a shorter bridge or a longer bridge? Well, if this moves 100 feet to get to the center and my other bridge went 175, that means it is also shorter. In length. Okay. And then what about this number out in front? What does that tell me? That's going to tell me how much I stretched my parabola, so how tall this bridge is. So this number on the front right here, that's 3 thousandths or 0.003, right? This number up here, my 58 over 30,000 number, if I write that as a decimal, it's 0.0018. So my first bridge, write that down, the first bridge is going to be a less steep cable. I could say has a flatter cable. Because it was shrunk more. So we could also go back and we could figure out like the heights of the towers, but I think I've got plenty in here. I've given some good comparison of them both being the same shape and they're both going up in the air, and I've given some good contrast, some examples of how they are different. Okay, let's go down to the last one. Part D says, in some bridges over canyons, the parabola is upside down. What notable change would this make in the function's equation? So you see here is our upside down parabola. How are we going to flip the parabola upside down? So the first number would have to be negative. Okay, and that would be on the outside. Oops. All right, let's turn the page. We got another word problem. Miss Ron drives to the library traveling at 40 miles per hour. She leaves home at time x equals 0 and arrives at the library 15 minutes later. As she pulls into the parking lot, she realizes that she forgot her card and instantly turns around to go home, also at 40 miles per hour. So we want to graph a model of Miss Ron's trip with the time in minutes on the x-axis. So this is going to be the time in minutes. And the distance to the library in miles on the y-axis. So this is my distance, and that's going to be in miles. So it says give the coordinates of 3 key points of interest on the graph. So let's see what we know. So I started out and I left home at time equals 0. So I don't know how far away I am yet, but I'm going to just say I'm far away from the library. My distance is the biggest it's going to be. And then I'm going to drive to the library, so my distance is going to get smaller. Eventually I'm at the library. It took 15 minutes for that to happen, right? So my time in minutes would be 15. And then I'm going to realize that if I got my card, I'm going to turn around. This, I know I'm at the same speed, so my slope should be the same. So where my trip would end would be 30 minutes from when it started, because it would take me another 15 minutes to get home. So this point right here, at the vertex of my V, that's a nice point. I can label that 15, 0, but I'm going to have to figure out for these points right here how high up I am, which means how far away I am from the library. So let's try and figure that out. So I was traveling at, whoops, sorry, my pen's not working, at 40 miles per hour in both directions. Now I have to be careful because my time is really traveled in minutes, but I know that 15 minutes is a quarter of an hour. So if I'm traveling 40 miles per hour and I'm traveling for 1/4 of an hour, then I should be going 10 miles. All right, so that means that I must live 10 miles from the library. All right, so B says, what are the real life domain and range for this function? So you notice my graph didn't have arrows on the ends. It stops and starts. So my domain would be my x values. My x values start over here at 0, and they continue for 15 minutes in either direction. So that was 0 is less than or equal to x, which is less than or equal to 30. And that would be the time in minutes. I'm going to write that down too, what it means. And then my range would be my y values. So I want to look at my lowest y value was down here at 0. In either branch, if I go on it, my top value was up at 10. So I have 0 is less than or equal to y, which is less than or equal to 10. And that is my distance in miles. Whoops. From the library. All right, what else do we have down here? Oops. All right, C says write the equation of the function to model Miss Ron's trip. So we know this is a V shape, so it should be an absolute value. So I know I'm going to have some sort of absolute value in here, and I got to do some moving. So where am I moving? This 15 moved the vertex of my V, the anchor point, 15 to the right. To move 15 to the right, I'd want to put a minus 15 on the inside. I didn't move up at all, so there's not going to be any number out here on the end. I also have to figure out what number would go in front right here of my absolute value equation to stretch me appropriately. So I can do this more than one way. I could count the slope, or I can plug in a number. I'm just going to go ahead and plug in a number for x and y. So I'll pick my y-intercept right here, my point 0, 10. So if y is equal to 10, then x should be equal to 0. So I would have 10 equals a times the absolute value of negative 15. Well, the absolute value of negative 15 is positive 15. So then I divide both sides by 15, and a is 10/15, or if I divide those both by 5, 2/3. So my final equation right here, let me scooch this up a tiny bit, would be y equals 2/3 the absolute value of x minus 15. Okay. Last part down here at the bottom. It says the next day, Miss Ron decided to walk to the library instead. When she got there, she realized that they were closed and immediately began walking home. Assuming she walked at a constant pace, how would the graph of her walk differ from her drive? So what's going to change? Is the distance from the library, the y numbers, are those going to change? No, they're not, because I still have to be 10 miles away from the library. But if I were walking, what would happen is I would be going slower, so it should probably take me more time. So this number is going to be, I'm just going to say, bigger than 15. Okay, if this were my minutes. It's going to be bigger than 15. It's going to take me longer to get to the library than it would. Okay, so how would the graph differ? So I could say the slope would be flatter, and the x-intercept would be further right. Okay, that should probably be a capital T, right? Okay, so I think I have one more question down here maybe. Okay, so it said what point would be the same on both graphs? So let me just sketch a loose little picture of my first graph up here. My first graph would look something like that. So the only thing they would really have in common is the start point for both would be the same, this 0, 10 point. So the y-intercept would be the same. Okay, our y-intercept is 0, 10. Would be the same on both. That's the only point that they would have in common. Okay, so let me know what questions you guys have in class and get ready for your test. Thanks.